binaries that you form and merge depends on the cluster mass as well. So here's the relation. So this is a I fit. So these are our simulated cluster models. And then you can see that for lower mass clusters, you have lower number of black hole binaries, and as you go higher, you have a higher number of black hole binaries as you go increase the mass. So big problem here is what are the mass of the most massive globular clusters, because your rates can change significantly if you have more massive models. So this is important. So this can change your rates by a factor of up to 3. So you can go from anywhere between 6 to 20 detections depending on this mass. So let me just put this here. So 6 to 20 events per parsec cube per year. So let me just sum up the conclusions. So globular cluster populations of black hole binaries are, they can explain that they're very likely to contribute to the population of black hole binaries in the universe. And just one more thing, so this is important with for the talk as well. So this is the, on the y-axis you have the rate, the merger rate density for different Chern masses as a function of Chern masses. And here you can see that the first observed observation was I think around 28 to 30 Chern masses, and this falls within our predicted Chern masses from the simulation models. So the peak is clearly here between 0 to 20, and then you have this long tail connected with very massive black holes that can form. So,
sorry, question with that.
Yeah.
So your axis there, the rate per cubic parsec per year per m sun, is that per m sun of the cluster?
Yes, that's for the cluster mass.
So if you have a cluster of 1 million solar masses, you expect a peak of 1 million cubic parsec per year?
No. Okay, sorry. There's something wrong with the axis.
I think that's probably per chert mass, just because you've divided that up.
Yeah.
When you're binning that thing, it's a
binning.
it's a histogram.
Yeah.
So
Okay.
Yeah. So, but these are all which we get. This is the distribution that we get from escaping black hole binaries. That's also important. So, what's important is that the rates are in the low end of the observed of the predicted values from LIGO and Virgo, and this depends a lot on the assumption of the cluster mass, the metallicity distribution, and then you have this tail of higher mass objects merging inside the clusters as well. So, thank you for your attention.
So I just got a question, partly associated with these rates. You did this with almost 2,000 models, including the ones that generated the IMBHs?
We did this, yes, including the ones we generated. But this is focusing on the escapers, so
right.
Most of them escaped quite early in the evolution. But not all the 2,000 models, only the models with mass fallback on. So
Okay.
These are around 900 models.
Okay, because the reason why I was asking that is I would expect that in the models that you have where you get IMBH formation, that you're in some ways artificially decreasing the number of stellar mass black holes that you have, assuming that the IMBH formation mechanism
is working properly.
Well, assuming the one that you have is enthusiastic, let's say, for producing IMBHs. So you may be able to increase the rates if you can figure out how to turn down the IMBH formation.
But so far, we are managing to form it in these dense systems, so
Okay.
so it's hard to find some condition which will remove that from the sample. Yes?
So
how do these compare with the ASIL's group results?
I think they have similar detection rates, similar merger rates, density as well. Yeah, I don't remember exactly. I think they have 5 to 15 or something like that. Yeah, so it's quite similar. But again, what the problem is again concerning with the masses that we use. I think they're extrapolating this fit to much higher masses than we are. So if we extrapolate to even higher masses, then we can even get more events, and then rates would increase more.
So this was the escapers?
This is, I think, the escaper. Yeah, this is the escaper.
And what's going on with those that are not?
that are left inside the cluster. Statistically, they weren't as many as the escapers, so we decided to focus the analysis on the escapers. But they have interesting masses as well. I think something similar to what you see here as well. Shapes are quite similar to the distributions.
Do you have a plot on the mass distribution of black holes independent of mergers?
Let me see if I can find one. I might have one somewhere. Let me see. I can retrieve them for you. Yeah. I'll find them and we can discuss that. Sure. Any other questions?
Maybe another comment just on the, when you were doing the relative field and globular cluster formation,
Right.
it looked like it was a factor of maybe 8 or 9 increase for low metallicity, but for the high metallicity is where you had the orders of magnitude increase.
Yeah, so this is
That one.
connection. So this is connected with the fallback prescription because fallback prescription depends essentially only on the metallicity. So the lower you have the metallicity, the higher the masses of the black holes you retain as well.
But I guess what I'm thinking here is when you get to the metallicity that's almost solar,
Yeah.
it looks like the globular cluster is producing 2 orders of magnitude more binaries
Yeah.
than it is when you have low metallicity. But I'm wondering if also in that case your higher metallicity ones are lower mass black holes.
They are.
Okay.
Yeah, they
So
definitely.
you might be producing lots more of them, but they may not be.
Dynamically, we are producing a lot more, but the masses are still in the, because of the lower, higher metallicity are lower.
Okay.